Woohoo! So mark your own. Good old Ann. And I did point out to you that for some reason the charges got chopped off. What can I ask you if I give you two charges? I could ask you for the force between them. I could ask you for the electric field at a location between the two charges. I could ask you, I didn't in this, but I could ask you how much potential energy that charge setup contains. I could ask you how much potential that charge setup contains. I think I did ask for that. Other stuff too, but those are some of the basics. Number one says find the magnitude of the electric force. So electric force in this unit, you know what? You may benefit from having your blue formula sheet out in front of you. You could have your yellow one, but if you have your blue one out, I'm going to be, again, rewriting certain equations and combining them. You could write that on your blue sheet as kind of study notes. You can't add them to your yellow sheet, but you'll know they're there. There are two equations that have a letter F in them. There's this one. K Q1 Q2 over R squared. And then there's this one, F equals Q times Z. That's the second equation. The second equation has E equals F over Q, and I got the F by itself. Taylor, how many letter Q's are there in this equation? How many letter Q's are there in this equation? I'm going to ask you the same question. I'm just going to phrase it slightly differently. How many charges do I require to do it this way? One. How many charges do I require to do it this way? How many charges do I have here? Two. Also, I think I told you the charges, I draw them round on purpose to give you a hint that the distance between them is a radius r circular. I'm going to use this one here. So it's going to be 9 times 10 to the 9th. 5 microcoulombs. Mr. Dewick, isn't it -5? So on your formula sheet, where you have all the equations under electrostatics, this first row, which is forces and fields, the first row, forget the signs. That's why I told you put absolute value signs. I did allow you to write that on your yellow sheet. So I'm not going to put the polarity, the positive or negatives in. Instead, I'm going to use like, unlike, attract. Sorry, YouTubers, I got a student who's a little dozy. And +3, I don't care whether it's positive or negative, I would just put the absolute positive value in. And it's going to be divided by 1.5 plus 0.85, 2.35 squared, is that right? I have no idea what this is going to work out to. Do you get 0.0244? I'm going to write it as 2.44 times 10 to the -2 newtons. 2.44 times 10 to the -2 newtons. I only asked for the magnitude. I didn't ask for the direction. If I asked for a direction, I'd have to tell you which charge we were talking about. What direction does charge 1 feel a force? To the right. What direction does charge 2 feel a force? To the left, because unlike attract. Okay, so I could ask you that. Or a good multiple choice question would be to have this in one column, and then next to it have what direction is the force on charge 1, charge 2. Do one of those chart ones where you go down each row and check marks and things like that. That would be a good multiple choice question. For 2 marks, I would probably go something like 1 mark for the equation, half mark for the numbers, half mark for the answer. As always, fair game, Dylan, would be if instead of me giving you both charges and the radius and saying find the force, I could give you the force and both charges and say, hey, find the radius, how far apart are they? Or I could give you, Courtney, the force, 1 charge, and the radius and say, find the other charge. Always forwards and backwards is fair game as far as I'm concerned. I would not give you A as a written question. Too easy. Too easy. If I gave you 3 charges and said find the net force on one of them, maybe. But even that's on the easy side. I would feel no problem giving you question B as a written question. I like question B. I like question B. Question B is a nice question. It wants me to find the electric field at location A. Each individual charge is sending out an electric field. Electric field is given by the letter E. And on my formula sheet, I have this equation, and I have that equation. I would use this to find electric field if I knew the charge at location A, because I know the force. I just figured it out. Although I don't know the force at location A, I know the force between the two charges. If, Ethan, I knew the force at location A and the charge at location A, I'd use the simpler method. I don't. In fact, what I'm going to do is I'm going to find the electric field from charge 1, magnitude and direction. I'm going to find the electric field from charge 2, magnitude and direction. The electric field from charge 1 is going to be kq1 over r1 squared. The electric field from charge 2 is going to be kq2 over r2 squared. It's going to be 9 times 10 to the 9th. Again, I ignore the negative. And the first distance was at 1.5? 1.5 squared. This might work out evenly. 9 times 10 to the 9th times 5, negative 6 divided by 1.5 squared. And I get 20,000. The units are newtons per coulomb. The units come from the second equation with the E in it. And here's the important thing, direction. Here's how I figure out the direction. I imagine a little positive right there, and I ask, which way would that tiny positive want to move if it could? Left. Or west, whatever you're more comfy with. Typically, I go left and right unless it's clear that I need to go two-dimensional. The second one is going to be 9 times 10 to the 9th, 3 microcoulombs, and this distance was 0.85 squared. By the way, what if there's no squared? What equation is that? That's potential, that's voltage. And yes, there is potential to get potential mixed up with potential energy, with electric field, with forces. I had to yell at my Block D class on Friday in love because it was pretty obvious that none of them had done any of the homework because I was asking basic questions and they didn't know anything. Do not fall behind in this unit. If you try and cram this unit at the end, all that's going to happen is on the day of the test, you're going to have E's and V's and F's all swimming in your eyes because all the equations look the same. And I'm sorry they all look the same, but that's the universe you live in, so live with it. Anyways, there is a squared. I don't think this is going to work out evenly. You get 37,370 newtons per coulomb direction. Also left? I'm going to add these vectorially. You know what? Since they're in the same direction, I can just add these in my head. It's going to be winner plus winner. Is it 57,400 newtons per coulomb left? Is that correct? If you got that, 2 out of 2. Otherwise, I would give you a half mark if I saw the 20,000, a half mark for that, a half mark for the magnitude, and a half mark for the direction. What else could I ask? I could have asked you to find the electric potential energy. Mr. Dewick, isn't that what you asked in Part C? No, I asked you to find the electric potential. Another word for which is voltage. Okay? So, how am I going to do that? I'm going to find the voltage from charge 1, magnitude no direction, because voltage is a scalar. I'm going to find the voltage from charge 2, magnitude no direction, because voltage is a scalar. And I'm going to add them up scalarly, not vectorially, because scalarville. Have I said scalar several times, Taylor? Here's how I remember. Scalars starts with an S. Signs starts with an S. For scalars, I'm going to include the signs. I'm going to include the positive or negatives. One of these is going to give me a negative voltage. Voltage potential is kq1 over r1, not squared. It's going to be 9 times 10 to the 9th, negative 5 microcoulombs divided by 1.5, not squared. Conveniently, I think I can just backspace, edit, and delete the squared. Oh, I got to include a negative now. And I get negative 30,000 volts. Charge 1 is giving a coulomb of charge sitting at location A, negative 30,000 joules of energy based on its location. Charge 2 is going to be KQ2 over R2. It's going to be 9 times 10 to the 9th, positive 3 microcoulombs divided by 0.85, not squared. I think I can bring that one back too and just delete the squared. And I get 31,765, positive 31,765. And if I add these up, volts. And if I add these up, it's going to be that number plus negative 30,000. And you get 1,760 volts. Okay. Before you turn the page, I would say to you, I would give you a half mark for that, a half mark for that, and 1 mark for the answer. Most common mistake, kids forget the positives and negatives. Scalars, signs. We turn the page. Number 2 is a good example of a written question I might ask you, as is number 3. Hedrick, what's number 2 wanting me to find? Work, you say. Well, that's going to be the change in potential plus the change in kinetic, although I think I'm going to ignore the change in kinetic because this question doesn't seem to be suggesting that this charge was moving before or after. On a test, I'd make that very clear. It would say something like, assume the charge begins and ends at rest. Hedrick, what's change in potential energy? What's change in anything? So this is going to be potential energy final minus potential energy initial. Let's see. Work is going to be K Q1 Q2 over R final minus... Where am I starting, Hedrick? It says an extremely large distance away. What am I really telling you? Where am I starting? Out at infinity. So what's my initial potential energy if I'm way out there at infinity? That's how we've defined potential energy relative to 0 at infinity. That made the question a bit nicer. If I wanted to make this question tougher on a test, I wouldn't have you start at 0. I'd have you start somewhere else, and you'd have an initial potential energy to deal with. For now, though, this isn't going to be too bad. It's going to be 9 times 10 to the 9th. The fixed charge is negative, and it's a scalar. I'm going to include the sign, 8 microcoulombs. They didn't tell me the second charge. Or did they? It's an electron. Help me out.
1.6 times 10 to the negative
1.6 times 10 to the negative 19 is wrong. Negative, because we're in scalars, signs. And that's important because what's a negative times a negative, Prith?
Positive.
I am going to get a positive answer that says I am going to have to do work, which makes sense. I'm moving the electron closer and closer to a negative charge. It doesn't want to go there. I will have to add some energy to this system. The answer will be positive. I'm positive. 0.15. 9 times 10 to the 9th. Negative 8 microcoulombs. Negative 1.6 divided by 0.15 divided by 0.15. Do you get 7.68 times 10 to the negative 14? Hedrick, final bit, units, work. Was it negative 14? Yeah, joules. Okay. For part marks, I would do something like this. I would give you 1 mark for that, 1 mark for that, 1 mark for that, 1 mark for the answer. What if you got it right 4 out of 4? Number 3. Lydia, what are they asking me to find in question 3? They're not asking me to find how much work, are they? So I'm not going to start out going work equals change in potential. In fact, if I turn my head sideways and treat this way as height, is there a change in height? Yeah. Is there a change in speed? Yeah. Is there a yucky curvy force? This is a job for conservation of energy. This is just like throwing something in the air, except in this case, stuff wants to fall up. So it's almost like dropping something heading down, except it wants to fall up. Okay. It's a little weird, but I can deal with that. So I'm going to start out going KE initial plus PE initial equals KE final plus PE final. It does say that we started at rest, so I can nuke that. I think the final speed is hidden in there, so I'm going to get the KE final by itself. I'm going to subtract the potential energy final over. I'm going to go PE initial minus PE final equals a half mv final squared. I could times by 2 divide by m. I'm going to do that at the very, very end. I'm actually going to evaluate this whole mess, Ethan, get an answer, and then go times by 2 divide by m square root. And I learned last class I have to write small because I ran out of room last class. It's going to be K Q1 Q2 over R initial minus K Q1 Q2 over R final. That equals 0.5 mv squared. You know what? To save myself a line, there we go. So I can go 9 times 10 to the 9th. Q1 is the fixed charge, positive 5.5 microcoulombs, and I would include the positive or the negative because we're in scalarville here. Are we moving a proton? 1.6 times 10 to the negative 19, positive this time, divided by our initial is 1. And then it's going to be minus same thing times same thing times same thing divided by, common mistake kids say, oh, isn't R final 2.5? No. 3.5. It's that distance there. Okay, don't let me trap you on that. That's a trick they will use on the test or on your written questions. 3.5, and that's going to equal 0.5 mv final squared. 9 times 10 to the 9th times 5.5 microcoulombs times 1.6 times 10 to the negative 19 divided by 1. I know I didn't need to divide by 1, but I'm sticking it there just so when I backspace and edit, everything's in place. I get 7.92 times 10 to the negative 15 minus, I repeat, except I change the 1 to a 3.5, and I get 2.2629 times 10 to the negative 15. That equals 0.5 mv squared. 7.92 times 10 to the negative 15 minus answer button. I get 5.657 times 10 to the negative 15. 5.6, what did I say? 57 times 10 to the negative 15. That equals a half mv final squared. Divide by 0.5 or times by 2. Divide by m. Gah! They didn't give me the mass. Or did they? It's on our sheet. I know it's 1.67. I can't remember the 10 to the 27. Thank you. 1.67 times 10 to the negative 27, and that gets me v squared by itself. So I'm pretty sure I'm going to square root. So it's going to be this answer divided by a half m square root. You get 2.6 times 10 to the 6th. Yes? No? Yep. So if you got that, what is it, 4 out of 4? I'd probably make this worth more than that on an actual test. For part marks, I'd probably go something like this. Half mark for that. Half mark for that. Half mark for that. 1 mark for the answer. That puts me at 2.5. I would give you a half mark if I saw that number. 3. Probably a half mark if I saw that. 4. And a half mark if I saw that. 5. But if you got it right, 4 out of 4. Can you give yourself a lovely score, please, out of 14? And then, if you could be so kind as to pass the quizzes inwards. Ready? So, we gave you this situation last day. Shh. I gave you the lesson, yeah? Okay. We said there will be an electric field between parallel plates. Which way do electric fields point? How do we figure out the direction of an electric field? Well, it's which way a positive would want to move if it could, so it's always going to point from positive to negative. Right now, please draw a straight line. Let's try that again. Draw a line like that. Draw a line like that right now. That's the direction of the electric field. Now, if I was going to draw the electric field, I would draw a series of parallel lines spaced equally apart. Oh, that one's a little too wide, isn't it? Because the distance the lines are apart reflects the strength of the electric field relative to that location. I think I said to you there's some curving and blurring of the electric field on the edges there. So, John, a good multiple choice question might be, I'll give you 4 pictures of electric fields and I'll say which one is the correct one. I guarantee one of the pictures would have the arrows pointing towards the positive, away from the negative. You would reject that. Or you might see it has something like this. And you would say, no, those set of lines that are closer together, that's saying the electric field for some reason got stronger there. That's not how electric fields work between parallel plates. They are uniform everywhere. I think I erased the wrong one. Here, let's do this, Mr. Duke. Oh, I did it, geez. Okay. Wow, did I botch that? There, ish. Ish. We said you could calculate the electric field by taking the change in voltage and dividing it by how far apart the plates are. That's review. Now let's talk about how lightning works. So, example 1 says this. Explain why an atom, this is not a parallel plate yet, explain why an atom will be ionized, lose an electron, if it's placed in a sufficiently large electric field. First of all, what's holding the negative electron in place normally? Well, what's the charge on the nucleus? Positive, unlike charges. So initially, there is a force that way. Let's call it force atom. F, that says F and then a subscripted atom. And that force is pretty strong. It holds the universe together. Does okay. But we have an electric field, an external electric field, a big electric field. Which way is this electric field pointing? To the right. Which way would an electron feel a force then?
To the left.
To the left, because electric fields tell us which way a positive will feel a force. So by logic, that means a negative will feel a force in the opposite direction. So this is going to create, this way, a really big electric force. And so if you bump your electric, and I can even tell you how big, it would be calculated, Courtney, by going QE. I got the F by itself in the second equation on my formula sheet there. I can bump that electric field up enough, Dylan, that I can have a big enough force that I can literally rip electrons off of atoms, okay? Let's call this one FE. So if FE is greater than F atom, will ionize the electron. Different elements, different chemicals, different atoms have different strengths of attractive forces around their nucleus. We're talking about air, which is mostly nitrogen and oxygen and other trace gases, but really mostly nitrogen. You can do this with about 3 million volts per meter. The electric field required is around 3 times 10 to the 6th volts per meter. And remember, volts per meter is the same as newtons per Coulomb. It's another way to measure electric field. 3 times 10 to the 6th volts per meter. That might seem like a lot. 3 million happens all the time. Taylor, you have had an electric field bigger than 3 million volts per meter if you've ever been taking clothing apart from the dryer on a dry, staticky day and you hear the crackling noise. Or if you've ever touched a doorknob on a dry day and got a shock, or lightning. All of those occur when the electric field in that vicinity was big enough to ionize the air, was big enough to rip an electron off from an air molecule and pass that electron on to the next air molecule, and rip the next electron off from the next air molecule, pass it on to the next one, and the next one. That's a current, because it's moving electrons. Each time this occurs, it's accompanied by light. We call it a spark. And the reason it's accompanied by light is because that ionized electron doesn't remain free. When it gets on to the next atom, it wants to settle down into a stable orbital electrical shell, but the only way it can do that is it has to get rid of some energy, and it gives off a photon of light. That's why we call it lightning. Okay. With me so far? So that's what's going on. If you can get an electric field bigger than about 3 million volts per meter. By the way, that means if you get a shock from half a meter away, that's 1.5 million volts. Half of that is about 750,000 volts. I have in Science 9 had the Van de Graaff generator giving shocks to kids with a spark about that long. That's about 200,000 volts they're getting there. It's not the voltage that does the damage, it's the current that does the damage. Okay? I already showed you last day the science project where the kid had Sale playing on his Tesla coils, right? So, good. Now let's link this to last day. Last day we talked about parallel plates. Kareem, I'm going to argue that you can think of a cloud and the ground as two roughly parallel plates. Now, it's true in real life, don't write this down, the bottom of the cloud is bumpy, but if we zoom out, it's roughly flat. And it's true that the Earth is curved, but if we don't zoom out too far, it's roughly flat. So we can treat this like a set of parallel plates. So here's what the question says. Suppose the bottom of a cloud is charged to 2.5 times 10 to the 8th volts. Let's label it. The voltage here is 2.5 times 10 to the 8th volts. That's the bottom of the cloud. We think this happens from cosmic rays passing through the cloud, through the atmosphere. John, we're still not quite sure, although I haven't looked at the latest research. 5 and 6 years ago, the cosmic rays was still a theory, but the numbers didn't quite match up with what we were measuring, and so, and it's tough to measure lightning because it's not like you can go up in the cloud and survive. So we're sending instruments up there, but they're getting massive shocks as well, and it's not like you can easily create lightning whenever you want it to repeat the experiment over and over and over and over. So the current theory is that the energy, you guys with me? Because voltage is energy per Coulomb, energy's got to come from somewhere. The current theory is that energy is coming from cosmic rays from outer space smashing into the atmosphere. Here's the question. How close does the cloud need to be to the ground for lightning to occur? Air breaks down at about 3 million volts per meter. In other words, we need an electric field of about 3 times 10 to the 6th volts per meter. What's this question want me to find? In English, what's it asking me to find? How, what? Close. I think, a distance. And they've given me an electric field and a voltage. Prith, is there an equation? Do I have distance, an electric field, and voltage in an equation? Yes. Oh, this is the electric field between plates, the one that you wrote on the previous page. The electric field between parallel plates is the voltage divided by the distance. What does this want me to get by itself?
Distance.
Times that there, divide that there, yes? The distance is going to be the voltage divided by the electric field. It's going to be 2.5 times 10 to the 8th, 3 times 10 to the 6th. I'll get volts divided by volts per meter. The volts will cancel and the meter will end up on top. What do you get? 83.3, if I recall. I didn't do that one in my head. I remember that answer. So, if the cloud is 100 meters above the ground, lightning can't quite make it. The really dangerous thing is if it's 85 or 86 meters above the ground, then it'll use you, because you'll complete the extra 2 or so meters that it needs. Okay? Or, if the conditions for lightning are really good and so this voltage gets higher, well, if this number gets bigger, you don't need as big a distance. Or, sorry, it can go a further distance. It doesn't need to be as close. The bigger the top gets, the bigger the distance can be. So, where would you not want to be in a lightning storm? Here's a picture. Where would you not want to be in a lightning storm? Based on what we just did. The boat, why? Okay, so boats are dangerous for 2 reasons. First of all, if you're a sailboat with a metal mast, you've just dramatically decreased the distance required for light, so the lightning can jump with a much lower voltage, still stuck with 3 million volts per meter of electric field needed, but the voltage can be smaller. Or, even if your boat doesn't have a mast, if the lightning hits the water, water's a pretty good conductor. It doesn't have to hit by you, it can hit near you, and you'll still get a pretty good shock. So this is one bad location. What else? Dylan, I thought you said something. Oh, I'm sorry. Where else? Why would the mountain be bad? You're right. It reduced the distance necessary. The lightning doesn't have to be, the voltage doesn't have to be as high, the cloud doesn't need as much energy, and it can still make the jump. If you're ever hiking in the mountains and you notice it's stormy conditions, and if you ever feel that the hair on your skin, on your arms, is starting to stand up, and this is me being serious, get out of there right now. Drop everything, sprint, and get to a lower altitude as fast as you can. You're probably within a few meters of height distance of having lightning be able to reach you. Okay, so if you're ever hiking somewhere, probably drop anything long and metal. If you have like a metal walking stick, chuck that. Do not raise it above your head and stick it in the air. Okay. Where else would be bad? Why would the tree be bad? The tree would be bad because the tree dramatically reduces the distance required for lightning to jump. And then the tree is a half-decent conductor. You would not want to be taking shelter underneath a tree because the lightning could then go through the ground to you. Probably the tree, you wouldn't get hit by lightning standing by the tree. The lightning would almost certainly hit the tree, but you'd notice it and then some. Put your pencils down, look up. You ready? I'd like you to recall that there's more than one way to find force in this unit. We started out with what we called Coulomb's law. This was the very first equation on your formula sheet, and that was the one that went K, Q1, Q2 over R squared. Kareem, I use that one when there's 2 circular charges and a distance between them. But if you move one equation over, there's another equation that has force in it. It's how we defined electric field. We defined electric field as force per Coulomb. If I get the F by itself, we get this. F equals Q E. You can write EQ, but I'm trying very hard to make this look similar to mg. What I want you to realize is mathematically, charge behaves an awful lot like mass did back in gravity, and electric field behaves an awful lot mathematically like acceleration did in gravity. Okay? So, let's take that and run with it. Hey, Priya, what does example 4 here want me to find? Yeah. No. Yeah. What does it really want me to find? How am I going to find acceleration? I think force. We have learned over our 2 years of physics many ways to find acceleration. Good gosh, lots of equations have an A in them. I think here, Priya, I'm going to write down A equals question mark, but I think I'm really going to spend I think I'm going to end up going like this. F equals ma. I think I'm going to go A equals F over m. And the reason I'm pretty sure is, what am I finding the acceleration of? An electron, and I know the mass of an electron. It's on my sheet anyways, not something. Okay? Priya, what's the charge on the top plate, positive or negative? Okay. Folks, this is a job for a free body diagram. Or, no, I think we're going to ignore gravity on an electron. I don't think we're going to do a free body diagram. I think we are going to say, Priya, there is a force pointing up. Okay? Which force is that? Electric force. Fe. Don't write this down. Kareem, my friend, how come I know that I can't use K, Q1, Q2? No, sorry. Taylor, my angel, how come I know I can't use K, Q1, Q2 over R squared? How many charges do I have here? 1. How many charges are there in this equation? So I'm not going to use that. The second equation that has an F in it, I'm going to rewrite it in my head to get the F by itself. I'm going to go like this. Where little q is the electron, and E is the electric field between the plates. Did they tell me the electric field between the plates? No. Wait. I have an equation for electric field between the plates as well, though. What? This is important, folks. Go look, find it. What's the other equation for finding electric field between the plates, which was what we talked about all of last day on Friday? Sorry? This new force equation between plates might be worth adding to your blue sheet as a little study guide. You might even draw some arrows. You might even connect, like you have this, right? I would probably add F equals QE and then draw an arrow from the E into there, whatever you want to do to stay organized so you know where it came from. But if I want to find the force on a charge between plates, it's that. I'm going to delete the box, though. Q. It's an electron. What's the charge on an electron?
0.6 times 10 to the negative.
Negative or not?
Not negative.
Because we're forces and fields, forget the signs. So we don't care. 1.6 times 10 to the negative 19. What's the voltage that it's traveling through? 275. Divided by, what's the distance? 2.5 centimeters. I'm not going to fall for that, so that's 0.025 meters. And I get a force of 1.6 times 10 to the negative 19 times 275 volts divided by 0.025. Do you get 1.76 times 10 to the negative 15? That's the force. But Priya, what did this question want me to find? Oh, I'm kind of running out of room, so I'm going to have to move up here. The acceleration is going to be the force divided by the mass. The acceleration is going to be 1.76 times 10 to the negative 15 divided by, Mr. Duke, they didn't give me the mass. It's an electron. So it's going to be this number divided by 9.11 times 10. And again, please make sure you know where those masses and charges are on your formula sheet. You can memorize them, but why bother? Do you get 1.93 times 10 to the 15th? Wait a minute. Isn't that faster than light? Was Einstein wrong? Because light was 3 times 10 to the 8th, and this is 10 to the 15th. Is Einstein wrong? Or was he? What did we find? Acceleration. Velocity? No. What did we find? If you actually calculate V final after 2.5 centimeters at that acceleration, you won't be going faster than light. You won't be. Not even close. You might say, well, Mr. Dewick, what if I let it travel further? What if I increase the distance? If you increase the distance, your electric field gets smaller comparatively anyways and takes care of you. Trust me, there's no setup that you can come up with here that will somehow have the electron going faster than light. The universe takes care of itself. Einstein was right. Okay? It's accelerating for such a short distance, it doesn't have anywhere near enough time to get to light speed. It's a big acceleration. Yeah. How did we get that 1.6 times 10 to the negative 19 coulombs on an electron? It was an experiment done by a scientist named Millikan. He used parallel plates to hold in place a charged oil drop. And he knew the mass of the oil drop. Using Avogadro's number, he knew how many electrons there were in the oil drop, so he knew the charge on the oil drop. And when he got on equilibrium, he knew gravity equals electric force, and he was able to solve for Q. You know what? Kind of like this. Example 5 says the charged oil drop below is at rest. Let's underline the word at rest. Due to balanced gravity and electrical forces. So what are the forces acting on this object? Get the obvious one.
Gravity.
It's at rest, so what direction must the electric force be pointing? Up. Has to be, right? Newton's first. Forces must be balanced. So I'll go electric force. By the way, if it's feeling a force up, is this object negatively or positively charged? Look at the way the voltages are set up. If it was positive, would it be attracted to the negative or be attracted to the positive? Okay, so I don't think it can be, I think it's got to be negatively charged because that's going to pull it up against gravity, right? Part A asks, what's the sign? And I've just explained to you, it's got to be negative, right? Positive would get sucked down along with gravity. Negative gets pulled up, gravity's pulling it down, and we fine-tuned this voltage very carefully so that it's in equilibrium, it's balanced. In fact, B says, write a balanced force equation. Okay. mg equals Fe. And I can use mg because we're near the Earth, we're not cosmic. I don't need to go big G, big M, little m. Don't do that. I'm not going to use kq1, q2 over r squared because Taylor's pointing out there's only one charge here. So I'm going to go mg equals qe. Now the question said for part B, write a balanced force equation in terms of the variables on the diagram. I don't see electric field on the diagram. What I do see is a voltage and a distance. Is there a way to write electric field as a voltage and a distance? mg equals q, change in voltage over distance. And when he did the experiment, Dylan, he was able to isolate q. And then since he knew how many electrons there were in his particle, he was able to give us the charge on one electron. It's been fine-tuned and improved since then, and I've really overly simplified what he did, but there's the gist of it. Example 6. A particle of mass 2.3 times 10 to the negative 14 kilograms and charge negative 3 electrons is held suspended between parallel plates. What's the voltage on the upper plate if we want to keep it in equilibrium at rest, if we want to have it hover there? What are the forces acting on this, Kareem? Get the obvious one. Which way?
Down.
If it's hovering, which way must there be another force? Has to be. That's our electric force. And in fact, we can start out again by saying electric force equals mg, or mg equals Fe. But I'm going to use QE equals mg. I'm going to use my second version of force where I know the charge that's experiencing the force and the electric field that it's stuck in. Except I don't know the electric field. Wait a minute. It's parallel plates. It's going to be Q, change in voltage over distance. That equals mg. What did this question want me to find, Kareem?
The voltage?
Oh, how will I get the V by itself? What will I do with the Q?
You would divide it.
What will I do with the D?
Times it.
Okay. So the voltage required is going to be M times G times D divided by Q. M, they gave it to me, not an electron this time. 2.3 times 10 to the negative 14. G, 9.8, we're back on Earth. The distance, 0.015, because they gave it to me in centimeters. What's the charge? Three electrons. I'm not going to put the negative in, I don't think. So 3 1.6s times 10 to the negative 19. How many volts will we need? I'm going from memory, not having done this in my head. I think you get something like 7,040?
Yeah.
That was purely from memory. Okay. Just giving you an idea of how we can start to combine everything. Today, particularly focusing on force. What's your homework? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Courtney? 1, 2, 3, 4, 5, 6. Skip 7. 8. 9, 10. That's it.